Oh, good. Okay, so let's get started then. Yeah, Melissa Maribel. I'm sorry, what was your name? Gina. Gina found Melissa Maribel on YouTube. She's got some good videos. If you want to see more examples worked out, or these things explained a different way than the way that I'm going to explain them here, or just to go back and refresh yourself on previous content. And I mentioned last week that I was going to post some stuff about some study materials, but I looked into it more. And the system seemed simple, but it was actually really complicated because it involves a lot of, you have to like build up a lot of information first and then really make your own system. But in talking with some other people over the weekend, I think really the best way to study is take your notes, and it's going to take a long time, but if you take notes in here and then take them home and then copy them into a separate notebook. Try not to do it verbatim too. The more you can like rewrite things in your own words, because the process of putting thoughts into sentences forces you to understand them and write them more clearly. And then write them as if somebody else was going to read them to try and learn the material.
So just like putting your own words back would go about solving that problem.
It's how you would solve the problem or different concepts too, right? So if you're writing down something about a limiting reactant, you know, I've got it written here as the reactant that is completely consumed or the reactant that makes the least amount of product. So when you're rewriting that, you might write, you know, limiting reactant, you know, it's the reagent that gets used up first, or it's the thing that you run out of. So even to just put it in those sort of terms, yeah. So yeah, that's sort of a summary though, just there of what we covered last week, talking about limiting reactant, theoretical yield, actual yield, and percent yield. And we have some more examples here too to go through, because we can use these four things to not only figure out what we're going to run out of, but it'll also help us predict and calculate how much we will actually produce given the certain set of conditions. So what are the limiting reactant and theoretical yield if you start with 1.8 moles of titanium and 3.2 moles of chlorine? So if we look at well, first look at our units, right? We're already in moles. So we know that on a chemical equation, all of these ratios, right? The implied one here, the 2 and the implied one here are in units of moles. So those are our mole to mole conversions. So first making that check, we know we're in moles. And if we just do, actually, let me double check here. Okay, it's going to be on the next slide. So we'll just talk through this first. So use stoichiometry then, right? That's that using those mole to mole conversions from our reaction equation to figure out how much we're going to make of either a product or another reactant. In this case, it's the product, titanium chloride. So we're going to use stoichiometry to find the amount of product that can be made from each reactant. So what we're going to do is we're going to start with titanium. And we're starting with titanium just because it's the first one listed here. You could start with chlorine too. Start with titanium and we'll calculate how much titanium chloride we could make with this amount of titanium. And then we'll come back and we'll say, okay, that's how much we could make with this much titanium. What about chlorine? If we're using this much chlorine, how much titanium chloride can we make? And in both situations, we're assuming that we have enough or more than enough of the other reactant. And then we'll pick our limiting reactant based on the one that gives the smaller yield. So if we go back to and try to remember to last Wednesday, which feels like so long ago, and think about making pancakes, right? If we don't have enough eggs or if we don't have enough flour, but we have more than enough eggs and baking powder, then we can't make more pancakes than we have eggs for. So in this case, we can't make more titanium chloride than maybe we have titanium for, or we have chlorine for. So yeah, our theoretical yield then will equal the smaller yield. So We're going to calculate this now, right? So what is the limiting reactant and theoretical yield if you start with 1.8 moles of titanium and 3.2 moles of chlorine? So we'll start out just like any problem when you're balancing a chemical equation. We have 1.8 moles of titanium. And then we're going to use that. If you remember too, just another recap, we're always going to go from moles to moles. And a lot of times, not in this example, but that involves going from grams to moles. And then we'll go to, maybe it helps to change colors here too, moles of something else based on our reaction equation, and then to grams. So that's sort of the outline really for all of these, and really every question in this chapter. And you just determine where you start based on the units that you're given and the units that you're asked for. So here, because we're given moles, we can skip this gram step. We're going to start with our moles. So our next step then, oops, erase this. Our next step then will be to get our conversion factor or a mole to mole ratio from our reaction equation. And since we're going from titanium to titanium chloride, we know we're going to titanium chloride because we're calculating a theoretical yield, which implies that we're looking for a product, but we're also given chlorine. So the only thing that we don't know anything about is titanium chloride. So going from titanium to titanium chloride, they both have a coefficient of 1. So then we can write out our, so 1 mole of titanium for every 1 mole titanium chloride. Okay, so we want to convert from titanium to titanium chloride. So we're going to put titanium on the bottom, because when we do that, we can cancel out our units of moles of titanium. And then we're converting into moles of titanium chloride. Yes. So we can do this still, right? Because it's for every 1 mole, we get 1 mole of titanium chloride. So that's the conversion ratio between the two. So it doesn't matter the quantity that we start with. It could be 1.8, it could be anywhere in between. It's like converting like centimeters into meters, right? If you're converting 100 centimeters into meters, actually, do a different number. If you're doing 114 centimeters into meters, so we wanted to go 114 centimeters to meters. The conversion factor between centimeters and meters is there's 100 centimeters for every 1 meter. So we would do 114 centimeters. This would be 100 centimeters, 1 meter. So we can have intermediate amounts. And again, remember, moles are, this is, if we were to convert this moles to atoms, it's 1.8 times 10 to the 23, or sorry, 1.8 times 6.022 times 10 to the 23. So we're converting a huge number of these, and that's why we use moles to make them convenient quantities to work with. Yeah, I'm gonna need this space. Right, so since this is converting 1 to 1, we don't really need to do any math, because if we multiply 1 mole by 1 mole of titanium chloride and then divide by 1 mole of titanium, we're going to end up with 1.8 moles titanium chloride. So that's the first part. Move this up a little bit. That's our first part. So now we've calculated, assuming that we have enough chlorine, how much titanium chloride would we make? Sorry, how much titanium chloride would we make with this amount of titanium? And now we need to do the opposite, because we need to see which one we're going to run out of first. So we're going to do our chlorine now. We're starting with 3.2 moles of chlorine. Mhm. That's it. These are really easy when it's moles to moles, and they only get a little bit harder when you go from grams to moles, because you have to figure out how to convert grams to moles using the periodic table. But it's just looking up some values, multiplying a few things. The difficult part is remembering every step. Yeah, it's the quantity of things, not the individual things that are difficult. Okay, so here now, we've got our 3.2 moles of chlorine. And then we go to our periodic table here. We see that we've got 2 moles of chlorine are required for every 1 mole of titanium chloride that we produce. So we have 2 moles chlorine for every 1 mole titanium chloride produced. Then again, we have chlorine as our units now, but we want to get to titanium chloride. So we're going to put our chlorine in the denominator so that when we multiply those, the units of moles chlorine cancel out. And we replace that with 1 mole or units of moles titanium chloride. So now we do have to do a little bit of math, but we have 3.2 moles. Again, on these, we multiply across the top and then divide by whatever's on the bottom. So 3.2 times 1 is still 3.2, divided by 2, give us 1.6 moles of titanium chloride. So which one is our limiting reagent? Yep. Yeah, exactly. So because we would produce fewer moles with this amount of chlorine, that is our limiting reagent. Because if we tried to produce any more titanium chloride, we wouldn't have any titanium left over. Or sorry, we wouldn't have any chlorine left over. Let me do this. All right, our limiting reagent then, the limiting reactant, titanium chloride. Right. Yeah, it's the one that you run out of first because it produces less. So this will actually be our limiting reactant will be, actually, sorry, the limiting reactant is chlorine. Our theoretical yield is 1.6 moles of titanium chloride. So it's your limiting reactant that always produces your theoretical yield. Any questions there? Yeah. Well, the key here is that we're only using 1 mole of titanium for every 1 mole of titanium chloride we produce, but we're using 2 moles of chlorine for every 1 mole of titanium chloride that we produce. So we need twice as much chlorine as we do titanium. So this especially gets sort of obscured when we're going from grams, starting with grams and ending with grams, because you start throwing molecular mass into the mix. So if you have 1 mole of hydrogen is just 1 gram of hydrogen. 1 mole of something like lead is 207 grams of lead. So there's a lot of ratios that get in, and it's hard to see from the starting amounts what you are going to run out of first. Yeah, so you really have to do both of them to see what you're going to get. Is there any other questions? There's questions on Zoom. I'll try to make sure I look over here occasionally to see if there's a chat. Okay. Moving on then. So we got another example here. So if you begin with 4.8 moles of sodium and 2.6 moles of fluorine, again, what is our limiting reactant and theoretical yield, but this time of sodium fluoride in moles? So it's pretty much the exact same setup. Actually, it is the same setup, exactly. All right, so we're given moles for both of these. So we know that we can just go from moles, use our mole ratio, and convert to whatever our final product is. So we'll start with, we'll just do 4.8 moles of sodium first. And again, I'm just picking that one because it's the first one listed. And then since we are already in moles, then we can just use our ratio here. So we'll have 2 moles sodium is required for every 2 moles sodium fluoride produced. And then we're going to cancel out 2 moles of sodium for 2 moles of sodium fluoride. All right, and if it's easy for you to recognize, we've got 2 and 2. So we're going to multiply by 2, divide by 2. So we don't actually have to do any math because we're still going to get 4.8 moles. But the key is that we've changed our units now from sodium to sodium fluoride. And then for our second problem, oh, yeah. Yes. Yeah, exactly. So this, if this matches this exactly, which is what we want, they cancel out. And so really you can think about this too is when we're doing conversions, really for anything, you can say that the number, as long as we're changing a number in the numerator, so on top, we put the number in the, or the units in the denominator that we want to remove. And then we put the units in the numerator or on top that we want to replace it with. So this is like subtracting it out, and then this is putting on top is adding it in. So for a second one here, 2.6 moles of fluorine. And again, we're just going to go to our reaction equation here because we're converting from moles of one element to moles of another element. We got 1 mole of fluorine for every 2 moles, sodium fluoride. So again, the unit that we want to remove here is moles of fluorine. So we'll put that in the denominator. We want to replace that with moles of sodium fluoride. So we put that in the numerator. Oh, that's right. I have the calculator on here. Okay. So we'll just do our 2.6 times 2. And then we would divide by 1, but we know that dividing by 1 keeps it the same thing. So we've got 5.2 moles of sodium fluoride. So we do this. So let's see, right? So we want a limiting reactant. We want theoretical yield. So which of these is our limiting reactant? Mm-hmm. 4.8 moles of sodium. Yeah, so we can highlight that up here too. It's our sodium that's our, well, actually not up here, sorry. because we have 4.8 moles of sodium, that's our limiting reactant. And so then our theoretical yield is always based on how much we can produce with our limiting reactant. So 4.8 moles of sodium fluoride is our theoretical yield. Any questions there? Okay. Well, let me know if you want me to stay on a slide longer. We've got time. Okay, so this is super applicable for industrial applications, where either the more costly reactant or the reactant that is most difficult to remove from the product mixture is chosen to be the limiting reactant. So you want whatever that is. If it's difficult to remove, you want to use it all up so you don't have to remove any. Or if it's really expensive, then you don't want to have to use as much of it. There's some reactions that are like, well, I guess it's a catalyst. Platinum is used as a catalyst in some reactions. And so you want that to be, use as little platinum as possible, or use as little of those expensive reagents as possible. And when we're working in the laboratory, we measure amounts of reactants in grams. Because again, it would be crazy to have a scale that measured moles. You'd have to tell it what you were putting on it. So to find limiting reactants and theoretical yields from initial masses, so that's the key here that we're changing now from just doing moles to moles. We're going to start going from mass to moles back to mass. As I called it last week, the gram witch. And so that'll add 2 steps to our calculations. But they're calculations that you've done before. So here, the key again, right, is that we have a different color for this. We have grams, we have grams. So we know that on our not periodic table, our reaction equation, these are all in units of moles. So we're going to have to convert first from grams to moles. Do this in a different color again. Moles to grams, right? Where the black is the element or compound that we're starting with, and red is the element or compound that we're converting to. So we can use this sort of as our solution diagram, just make it a little bit more specific. But again, we just do it almost exactly the same way that we did before when we were just working with moles. We just add this extra conversion in. So we'll start with 53.2 grams of sodium. And then the atomic masses from the periodic table are all in grams per mole. That's why we can use them to convert from grams, which we have here, to moles, which we need. Let's see, where can I put this? That's out of the way. Move this up here. So for sodium, move this farther over a little bit. Still on the screen, yeah. For sodium, because we're just working with sodium, we just look at the periodic table. It's 22.99. I'm going to round that for the sake of saving space. On an exam, you'll be given a periodic table. You should use the full value that's given on the periodic table, which will usually be 2 decimal places. So this is 22.99 grams per mole of sodium. Draw this line. All right. So now using our atomic mass, we can convert from grams of sodium to moles of sodium. So we have grams on top already, so we want to put our 22.99 grams of sodium on the bottom because grams is the unit which we're trying to remove. And then the atomic mass is how much mass you have for every 1 mole of substance. So, oops, that's not grams. 1 mole sodium. And then we've now gone from grams to moles of sodium. And we're looking for a theoretical yield, so we're converting it to the product. So now we're going to go from moles of sodium to moles of our product, which in this case is sodium chloride. It's going to be 2 moles sodium for every 2 moles sodium chloride. And again, this is a 1-to-1 ratio, but we're going to put it in there so we can see where our unit conversions are happening mostly. So 2 moles sodium, again, removing this unit from our previous step, and then adding in 2 moles sodium chloride. Oops, CO. And the final step will be to convert from sodium or moles of sodium chloride to mass of sodium chloride. So it's not enough space. Oops. Let's do it like this. So the atomic mass of chlorine is 35.45. Scam likely, nice. Grams per mole chlorine. So then the molecular mass, right, as opposed to the atomic mass of sodium chloride is going to be the mass of sodium plus the mass of chlorine, because that's what makes up sodium chloride. So it's going to be, whoops, 22.99 plus 35.45. So 58.44. And now we're converting into grams. So we're going to be removing 1 mole sodium chloride. We're really removing moles of sodium chloride, replacing it with 58.44 grams sodium chloride. So then our final answer will be in units of grams sodium chloride. Right. And we just added them together, didn't multiply anything because we only have 1 sodium and 1 chlorine for every sodium chloride formula unit or molecule. So then we can do, we'll take our 53.2, right, our initial mass of sodium, and then we can multiply across the top. So I'm going to skip multiplying by 1. We can multiply by 2, and then multiply by 58.44. And then we'll divide by all the numbers on the bottom. So, right, that's a huge number, but we'll divide by 22.99, divide by 2. And then, right, we don't need to divide by 1. Just skip the ones. So we'll end up with 135. It's 135 grams sodium chloride based on this amount of sodium. So that's just part 1, because we want to determine the limiting reactant and the theoretical yield. So we need to be able to compare that to how much we would make with this amount of chlorine. And I'll move just a little bit faster here because it's the same steps. So we're going to have 65.8 grams of chlorine. One easy way to get tripped up is to forget that chlorine, it's written out for us here as Cl, right? That subscript 2 means there's 2 chlorine atoms. So I'll actually do 35.45 plus 35.45, or you could multiply by 2, you'll get the same answer. This will be 70.90 grams chlorine for every 1 mole of chlorine. So this is just the molecular mass of chlorine. 35.45 times 2. So for this chlorine, yeah, for this chlorine molecule, we have 2 chlorine atoms. So that doubles our mass. And then our next step here will be to convert from moles of chlorine to moles of sodium chloride. So because we have moles of chlorine, or actually, let me write this out. Right, so for every 1 mole chlorine, Cl2, we can produce 2 moles NaCl, sodium chloride. So then, because we want to go 2 moles of sodium chloride from moles of chlorine, we'll put 1 mole of chlorine in our denominator. We'll put 2 moles of sodium chloride in our numerator. And then the silver lining for these problems is that once you've done one of them to convert to your product, you already have the molecular mass of what you're converting to for your second one. So that part ends up being the same. This will be 58.44 grams sodium chloride, 1 mole sodium chloride. So then just starting at the beginning of this, we're going to do our 65.8, and we're going to multiply by 2, and then 58.44 times 2 times 58.44, which will equal that. And then we'll divide by 70.9. And then these other 2 are just 1s, so we don't need to divide by those. So we'll divide by 70.9 to get 108 grams of sodium chloride. So then our limiting reactant is going to be 65.8 grams of chlorine. And our theoretical yield is going to be 108 grams of sodium chloride. Any questions on that one? Okay. Yet another example. So let's do another example coming up still too. Let's try and do something a little bit different with this one and start out by writing out the steps that we're going to take as we go through this. So the first thing that we need to do is check the units. After determining that it's a theoretical yield problem, which this one uses slightly different terminology, but it asks what's the maximum amount of ammonia in grams that can be produced or synthesized. And so this is a synthesis reaction, taking 2 things and combining them together. From this mass of nitrogen and this mass of hydrogen. So the tempting thing here would be to look at this and say, what's the maximum amount? Let's go back to this previous problem, right? If this asked us what was the maximum amount of sodium chloride we could produce, it would be tempting to look at this and say, oh, I could produce 135 grams of sodium chloride. But that's not the case because we would run out of chlorine before we could get to this amount of sodium chloride. So something asks you, if I ask you, what is the maximum amount you can produce? That's sort of a key word there that it's a theoretical yield problem. So you're going to be looking for your, well, first your limiting reagent, and then that will tell you what your theoretical yield is, and thereby the maximum amount. It's like the most number of pancakes you could make given these ingredients. What's the maximum number of pancakes? What's the maximum amount of compound? So once we've determined, really that's the first step, right, that this is a theoretical yield problem, we want to check our units. Because if we're given units of, if we're writing this down again, grams, moles, to grams. I always write this as the core because these are, at the very least, you're going to use moles to moles. If you're not using just moles to moles, you're going to have to go grams to moles, but you might sometimes have to go a step further from some other unit to grams. So we'll first check our units. We'll see that we're working in grams, and we've been asked for a mass in grams. Okay, so we know that we're going to be using this section of our sort of general reaction diagram for a limiting reagent problem or stoichiometry problem. The second step is going to be then to calculate the yield for each product that we're given masses for. I guess this would be like a subheader underneath this. So the first step there would be convert from grams to moles. And that to do that, we're going to need, to do that, we're going to need our atomic mass. And we get that from the periodic table. Then B, we're going to go from moles to moles. And we'll get that using our, sort of in the name there, but mole to mole ratio. So this one comes from periodic table. This one comes from our, I'm just going to use abbreviations here, our reaction equation. And then C, we're going to go back from moles to grams. And again, that's using atomic mass, whether it's the mass of a single element or the mass, calculated mass of a compound. And we'll get back to grams. And then for a final step, will be to find the least product produced. Okay. I'm going to need all of this space, so I'm going to shrink this. Put it up here. Might be too small to read now, but I'll post the annotated lecture slides today after class for chapter 9. So you'll be able to come back and look at all this in the PDF. All right, so we checked our units, we've got grams. So we know that when we go to calculate our yield for each of these, we're going to go from grams to moles first. We know that we're going to use the atomic mass that we get from the periodic table. So we start with 25.2 grams of nitrogen. And again, picking nitrogen because it's first in line. These don't have to be done in a particular order. Okay, so then we want to go from grams to moles. So for nitrogen, this is N2. So the mass of nitrogen is going to be 14.01 grams per mole nitrogen for a single nitrogen atom. But do you guys talk about the diatomic elements? There's like the one I use is Brinkelhoff, but I think there's one that's like horses and oats and clear brown eyes. Yeah, I can't remember that one, but Brinkelhoff's the one I can remember. So it's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. So all of those 7 elements, when they exist as their elemental form, are diatomic. I haven't heard that one before, but I like that one a lot. Have no fear of ice cold beer. Good. Yeah, whatever, mnemonic that you use to remember it. But here we have nitrogen, which is one of those. So when we calculate our atomic mass, right, based on 2A here, it's going to be 14.01 times 2. Because we have 2 nitrogen atoms, 14.01 times 2. So 28.02. 28.02 grams of nitrogen for 1 mole nitrogen. And then we want to convert from moles to moles. And going from moles of our reactant that we're interested in to moles of our product. In this case, we have a single product, so that makes things a little easier. We'll say that you might get problems where there are 2 different products. In that case, you only need to calculate for one of those products, because the amount of one product that you make is linked to the amount of the other product that you make. You just need to make sure you do the same product for both reactants when you're calculating a limiting reagent. For now, though, we just have the 1. So we're going to go from nitrogen, right, because we're starting with nitrogen here, and then we're going to ammonia. So we're going to do 1 mole of nitrogen is required for every 2 moles of ammonia that we make. So we're at units of nitrogen here. So we want to convert that 1 mole nitrogen, 2 moles NH3. So, and actually I could do this maybe. Right, so this is going to be 2A. This is 2B. And our last step will be 2C, according to this chart that I wrote out. Because now we have moles of NH3 as our units. And we're going to convert from moles of NH3 to mole or grams of NH3. So we'll need the atomic mass of hydrogen, which is 1.01 grams per mole. Remember, these that I have written up here are just their values from the periodic table. So we'll need to calculate then for ammonia what our molecular mass is going to be, right? So atomic mass for a single atom, molecular mass for the molecule. So then our ammonia is made up of a single, whoops, let me just delete everything, a single nitrogen and 3 hydrogen atoms. So the mass will be 14.01, the mass of hydrogen, or the mass of nitrogen, plus 1.01, the mass of hydrogen, yep, times 3. So 17.04. And now we're converting 2 grams, 17.04 grams NH3 for every 1 mole NH3. So we can finish this off then by calculating the mass. So 25.2. Again, we're multiplying across the top. So multiply by 2, multiply by 17.04. Give us that number. And then we'll divide by 28.02. But we won't divide by anything else because we have 1 and 1 as the other numbers in our denominator. So our answer then will be, well, the answer for this will be 30.7 grams NH3. I just rounded 30.65 since that last digit was a 5, or the digit before the last digit, the 5 we round up. 30.65 or 30.7, sorry. Okay. So good, we did one of them. And now we just kind of rinse and repeat and do that now with our second compound of interest, hydrogen. So we're starting with 8.42 grams H2. No. Yeah. Doesn't matter which one you start with. I just start with whatever one is first in line. Or first in the question. Yeah, you can start with either. Okay, so similar thing here, right? Hydrogen is again one of our diatomics, very conveniently written out here correctly for us. So we're going to have 2 hydrogen atoms. So we'll take our 1.01 and multiply by 2. And that will give us 2.02 grams of hydrogen for every 1 mole hydrogen. Right, so that's 2A. Now 2B is to go from moles to moles. We'll use that ratio from our reaction equation. So we have 3 moles of hydrogen are required for every 2 moles of ammonia that are made. Three moles hydrogen, 2 moles ammonia. And that makes sense too, right? If you look at this, both sides of our reaction equation need to be balanced. So this 3 times 2 gives us 6 hydrogens. 2 times 3 means that there are also 6 hydrogens on the right side of the equation. That's what these ratios help balance. It's 2, 3. So then we're, again, and this is, you might be tempted to look at this and say that, oh, we always take the ratio from these ratios, we take the one on the left, we always put that in the denominator, and we take the one on the right, we always put that in the numerator. But it depends on how you write this out, because we could write it either way. So just remember, we're using this one, not because it's on the left, but because it's moles of hydrogen. So it's going to be 3 moles of hydrogen. On our denominator, 2 moles ammonia in our numerator. And again, since we're both converting both of these into grams of ammonia, we already have from our first problem, from our first calculation, the molecular mass of ammonia. And since we are again going from moles of ammonia to grams of ammonia, you can really just copy that down. So we have 8.42 times 2 times 17.04. Give us that. And we'll divide by 2.02. We'll also divide by 3. Give us 47.4 grams of NH3. So again, oh, right, it's not specifically listed here, right? But we're looking for the maximum amount of ammonia. So we've been using blue for theoretical yield. So which of these is we've been using blue for the limiting reactant. So which of these is our limiting reactant? Right. Nitrogen's the limiting reactant. So that means that the amount of ammonia produced by that amount of nitrogen will be our maximum. Yep, 30.7 grams. Any questions on that one? $30.7, yep. So the theoretical yield is also the maximum amount that can be produced. Okay. Let's see if there's anything else. Oh, right, enthalpy. Okay. I'll have to check real quick. I forgot to check if enthalpy is in your book. I think it might be. Okay, so we have iron oxide reacting with carbon monoxide to produce iron and carbon dioxide. This is, well, let's identify what type of problem we're looking at here. So we see that the reaction of 185 grams of iron oxide with 95.3 grams of CO2, or sorry, CO, carbon monoxide, produces 87.4 grams of iron. What we're asked for is the limiting reactant, the theoretical yield, and the percent yield. So one of the key things, let me highlight these, right? Reactant, theoretical yield, and percent yield. So you might look at this, say, oh, well, we've already been told it produces 87.4 grams of iron, but that is going to be our actual yield. So there's a reason that this is a theoretical yield. Based on the numbers of atoms present, we can recombine them to get a maximum amount, a theoretical amount of iron based on our calculations. But in the real world, most reactions don't go to completion, and you get some left over for one reason or another. And so your real world values will often be different than the values that you would calculate that you might get, that you might yield if you actually did the experiment. So in a problem like this, know that if you're asked for a limiting reactant theoretical yield, percent yield, and you're given a value, because you have to be given a value from the real world sort of experiment to calculate a percent yield, that again, you're going to be doing a limiting reactant problem. So we're going to have the same basic steps that we talked about before. We've identified that we have a limiting reactant problem. For one, we're asked to calculate it. But we'll start in the same way that we've started them all. I'll ask to write out 185 grams of iron oxide And actually here, this is important too, I suppose. We're going to be using the iron oxide and carbon monoxide and calculating the limiting reactant and theoretical yield between those two, because those are our two reactants. So, right, it's a limiting reactant, has to be one of the reactants. And let me ask this question as well. Okay, so we're calculating how much of the product that we're going to make. Which product do we want to calculate for and why? Are we going to calculate the amount of iron we're going to produce, or are we going to calculate the amount of carbon dioxide that we're going to produce? Well, it's not the carbon dioxide. You could, we'll say this, you could calculate for carbon dioxide, and that would tell you what your limiting reactant was, but it would only tell you your theoretical yield of carbon dioxide. I guess this isn't incredibly clear, but we're given a mass of iron. So we're going to calculate the theoretical yield of iron, because what's given here is, and I'll be more clear about this in exam questions, this is like an actual number. Like if you were to actually go out and do this, you would get some yield less than your theoretical. So actually, let me write this out too. So to calculate percent yield, because that was something that we talked about last week, percent yield is going to be an actual yield minus theoretical divided by the theoretical. And then times 100%. So that's one, I think it even says on the slide there, the previous slide where we talked about that, which was last week. So very easy to just let that one slide by with all the stuff that we cover in every class. But to calculate a percent yield, you need an actual yield. And so we can save ourselves some time, because we could calculate for CO2, figure out what our limiting reactant is, then calculate the amount of iron that would be produced using that limiting reactant. But why do that when we can just use iron? And you'll see that we'll get a number that's larger than 87.4, and we should. Okay, so iron, the periodic table, and we're going to need oxygen. We're also going to need carbon. So for iron oxide, we just need iron and oxygen. Iron is 55.85 grams per mole iron. Oxygen, 16.00 grams per mole of oxygen. And carbon is 12.01 grams per mole carbon. So our molecular mass of iron oxide, right, because our first step is we want to go from grams to moles. It's the first side of our Graham-Witch. We're going to do 55.85 times 2, because there's 2 iron atoms in our iron oxide. And then we'll do plus 16.00 times 3, because we have 3 oxygen atoms in iron oxide. So our total molecular mass will be 159.7. And that's 159.7 grams of iron oxide per 1 mole iron oxide. Carbon we don't need for iron oxide, but I wrote it on there because we'll need it when we calculate. Oh, actually, yeah, we'll need it when we do CO2. So I'm just writing down the ones from the periodic table here. So then to go from moles of iron oxide to moles of iron, which is where we want to get to, we'll need that ratio. So that'll be 1 mole iron oxide for every 2 moles of iron. Maybe again, we're going to put iron oxide in the denominator here because we're going to cancel. We want to cancel those units out to replace them. And 2 moles of iron because that's what we want to replace those units with. And then finally, we'll go from our moles of iron now to our grams of iron. So because iron here is just the atom by itself, we can use just its atomic mass, which we grabbed from the periodic table earlier. So 55.85 grams of iron for every 1 mole of iron. So then it's 185 times 2 times 55.85 divided by 159.7. And then the rest of those are ones. So we'll get 129. Oops. Yeah, 129 grams of iron. So if iron oxide was our limiting reagent or limiting reactant, then we could produce 129 grams of iron. But we're not done yet. Now we're going to start with 95.3 grams of carbon monoxide. We're going to calculate, based on 95.3 grams of carbon monoxide, how much iron could we produce, assuming that we had more than enough iron ore. So our first step is to convert then from grams to moles. So carbon monoxide is just a single carbon, 4.01, plus a single oxygen, 16.00. We get 28.01 grams of carbon monoxide for every 1 mole of carbon monoxide. And then we want to convert from moles of carbon monoxide to moles of iron. We want to convert to the same thing because we want to be comparing the same thing. All right, we want an apples to apples comparison, not an apples to oranges comparison. So we look at our reaction equation then to get our mole to mole ratio. And we can see that for every 3 moles of carbon monoxide, we can produce 2 moles of iron. So we want to get rid of moles of carbon monoxide so that we can convert to 2 moles of iron. Oh, I'm sorry, I didn't write that out. Right, so 3 moles carbon monoxide for 2 moles of iron. And as our final step, we'll convert that moles of iron to grams of iron. And we can just copy that from our previous calculation. That's 95.3 times 2 times 55.85 divided by 28.01 divided by 3 will give us 127, rounding up there, grams of iron. Let's try and move that over a little bit. Okay. So you can see that based on the quantities that we were given, they both calculate out to more than this yield from the actual reaction. From the actual reaction used to produce iron. So this is where now we're going to use our equation up here for percent yield to calculate what the percent yield is. And first, I guess, which one is our limiting reactant? So our limiting reactant then is carbon monoxide. But yeah, that is our theoretical yield, 127 grams of iron. And then we can calculate our percent yield. So I'm going to take our actual, which is what we were given, 87.4 grams iron, minus our theoretical, 127 grams of iron, and divide by our theoretical, this, right, and then we'll multiply that by 100% to get a percentage. So we'll do 87.4 minus 127. What's that? Divided by 127. And then we multiply by 100. So then our percent yield is 31.2% yield. Actually, a negative 31.2%. Wait, did something backwards. Oh, I'm sorry. I calculated percent error. Percent's just the percent yield is the actual divided by the theoretical. I'm sorry. This is percent error. Well, okay, let's. Okay, sorry, yeah. Percent error is the actual minus the theoretical divided by the theoretical. Percent yield is your actual divided by the theoretical. So this will be 87.4 divided by 127. That's better. Times 100. And we'll get, I'll write it down here still, 68.8% as our percent yield.
someone to figure out 3 different answers, your reactant, your theoretical, and then your synthetic.
Right. But you could get a question that just asks you for percent yield. And you would still have to calculate. Right. You do all that and then just have the single answer at the end. Because every step is required to get to there. Okay, that is it for today. Are there any other questions? Canvas. Yeah, so I have if you're on Canvas, you go to Pages. There's, I think the page is called Lecture Resources. And so I'll just continuously update that as resources become available. And then I'll post an unedited version of the class as soon as I get home of the lecture. Cool. I believe so.